We'll get started up here with the next block of questions. So question 8 is up next from the practice exam. The freezing point of a 0.3 molal lactose in water solution. All right, so our change in freezing point equals our negative Van Hoff Kf times our molality. So my change in freezing point equals lactose is a molecular compound, so it's going to have a Van Hoff factor of 1. And then who knows our freezing point constant of water? Yep, 1.86 degrees Celsius per molal. So we multiply all of these together, 0.3 times 1.86. And I get a change in freezing point equals negative 0.558 degrees Celsius. Our normal freezing point for water is 0. So we subtract, 0.558 degrees from that to see that, here, this step is not as important as it is for the boiling point elevation, but, 0.56 degrees Celsius, negative 0.56 degrees Celsius would be our new freezing point for this solution. And again, just be careful if your molality is different, the steps would still be the same. Lactose is still going to have a Van Hoff factor of 1. If your molality changes, right, we would just change that number right there. Nope, 1.86 is a constant. It's positive. What's negative is in the equation. It's a negative in front of the Van Hoff factor. And then Olivia, yeah, I would give you the freezing point and boiling point constants for solvents. And if we used a different solvent than water, I would give you the normal boiling point or freezing point. Question 11. The solution that has the lowest vapor pressure, right? Very similar to an earlier question that we looked at. The solution that has the lowest vapor pressure is going to have the highest boiling point. And if we look at all of these are molecular compounds, right? They're all carbon, hydrogen, oxygen, carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. So non-metal, 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 all molecular compounds. So they all have the same Van Hoff factor. So when they're all having the same Van Hoff factor, right, our change in boiling point equals Kb times our molality. Okay, good. Sorry about that. Molality is the same, boiling point constant's the same, or Van Hoff factor is the same, boiling point constant's the same. It's going to come down to which one has the largest molality. That's going to have the largest increase in boiling point and therefore the lowest vapor pressure. So choice F there. $12, $13, big questions here. All right, question 12. A bottle of wine is 12% ethanol volume by volume, which means if you had 100 milliliters of that solution, 12 milliliters would be ethanol. Or if you had 1,000 milliliters, right, you'd have 120 milliliters of ethanol in that solution. Ethanol, right, ethanol is just CH3, CH2OH, so it's a molecular compound. So it would have a Van Hoff factor of 1. The moles of ethanol, okay, so for that we have to do a little bit of math. I've got a 1.5 liter solution, so 1.5 liters is 1,500 milliliters, and 12% of that by volume is ethanol. So yeah, and then half again. So I'd have 180 milliliters of ethanol. And that means of the 1,500, right, we subtract 180 and I'd have 1,320 milliliters of water in this solution. So now we can start to find moles because I know the volume of ethanol is 180 milliliters, and I know the density of ethanol is 0.789 grams per 1 milliliter. So 180 times 0.789, got 142 grams of ethanol. All right, the molar mass of ethanol, I've got 12, 24 plus 16 is 46 grams per 1 mole. All right, so we've got like 3.08 moles of ethanol. The molality of the solution, so molality now is mole 3.08 moles, and that is where I bring in the milliliters of water, right? Water density of 1, so 1,320 milliliters is 1.32 kilograms, right? It would be 1,320 grams, so change that to kilograms. So divide that by 1.32, and my solution is 2.34 molal. So now we can find the freezing point, right? The freezing point, our change in freezing point equals negative Van Hoff Kf molality. My change in freezing point equals my negative Van Hoff factor is 1, my freezing point constant 1.86 degrees Celsius per molal, my molality 2.34 molal. Multiply all of that together times 1.86, and I get a freezing point of negative 4.35 degrees Celsius. Subtract that from 0 because it's an aqueous solution, right? And my final freezing point would be just that, negative 4.35 degrees Celsius for question 12. Question 13 is very, very similar, right? The ocean contains 34.2 grams of sodium chloride per 1 liter of water. That means how many moles of sodium chloride? Well, got 34.2 grams, and I've got 58.44 grams in 1 mole of NaCl. 34.2 divided by 58.44. I've got 0.585 moles of NaCl. For a molality of, so there's the tricky part, right? A lot of people were just dividing by 1 kilogram because we have 1 liter, but again, in this solution, number one, the question could be a little bit better because they could give you the density of salt water. It's not going to be the density of water for this question. So I would say there's a slight problem with that. So we'll just say if it has the density of water, we'd have 1,000 gram solution, and of that 1,000 gram solution, 34.2 grams of it are sodium chloride. So my solvent, my actual solvent, is, right, 965.8 grams of water. But again, I think they should have given us the density for a better calculation there. So the molality of this, right, 0.585 moles divided by 0.9658 kilograms of water. 0.5 divided by 0.965. All right, I get 0.606 molal. So I think that's why a few people were getting this one wrong. So they were just using 1 kilogram. And we have to take into account that it just wants the mass of the solvent and not the mass of the solution. So now our boiling point, right? Delta TB equals my Van Hoff KB times my molality. So my change in boiling point equals my Van Hoff factor for sodium chloride is 2. My boiling point constant is 0.52 degrees Celsius per molal, and my molality is 0.606. Multiply those all together times 0.52 times 2. And yeah, not a whole big change, but 0.63 degrees Celsius. So I add that to 100, right? That would make my final boiling point like 100.6 degrees Celsius for question 13.